Hello everyone, and welcome to another episode of Math-221. Today we're going to talk about section 10.2, which is trails, paths, and circuits. Okay, so to start off this lesson, we're going to look at a motivating example, the earliest problem in graph theory, which is the 7 bridges of Königsberg. So the question here is, we're in a city called Königsberg, which is actually in Russia, and we want to know if there's a way to take a walk that begins and ends at the same point and crosses each bridge exactly once. And you can see in the map there that there are 7 bridges, and there's also 4 land masses. There's the 2 sides of the river, A and D, and then there's B and C, which are islands in the river. So we can actually transform this problem into a graph where the land masses are represented by vertices, and then the bridges are edges. And so we can talk about moving around on this graph and ask whether there's a way to walk around the entire graph, going over every edge exactly once, that begins and ends at the same point. So for example, I could try to start here at C, and I could go to A, and then I could go to B, and then if I go back to C, then maybe I could go over to D, and then I could go to B, and then I could go back to A, but then I would have to cross one of the bridges more than once to get over to this bridge that I hadn't crossed before. So this is a little bit tricky, I think. I believe there is actually not a way to do this, but you can play with it yourself if you want to find out. So this might seem like a trivial problem, but these kinds of problems are actually really important in shipping and logistics. You can think about the idea of like a delivery driver who wants to visit every house on his route exactly once in the most efficient way possible. So there are a lot of graph theory problems related to these ideas. Okay, so let's get into some definitions. This slide contains an intimidating amount of definitions, I think. So all of these definitions here are about moving around on a graph. So let G be a graph, and let V and W be vertices in G. Then a walk from V to W is a finite alternating sequence of adjacent vertices and edges of G. So it's basically exactly what it sounds like. You're going to walk around on the graph, and you can go wherever you want, and then you just have to write down where you've gone. And so you just alternate between a vertex and then an edge and then a vertex and then an edge, and just keep on going like that. Vertex, edge, vertex, until you get wherever you were trying to go. So all the V's there in that list represent vertices, and the E's represent edges, and then V0 is V, which is where you started at, and then Vn is W, which is where you wanted to end up at. Okay, and then each of those edges there has its endpoints, like the endpoints of E1, for example, are V0 and V1. I mean, obviously you can't go from V0 to V1 via E1 unless E1 is the edge that connects V0 and V1. And then we can also have a trivial walk from V to itself, which just is basically just standing still. So that would be a trivial walk because it doesn't involve any walking. Okay, and then let's look at some of these other ones. So these are types of walks. So a trail from V to W is a walk from V to W that does not contain a repeated edge. It can contain a repeated vertex, but not a repeated edge. A path from V to W is a trail that does not contain a repeated vertex. Now, if you think about this for a minute, you'll realize that if you don't have any repeated vertices, then you also don't have any repeated edges. Because if you repeat an edge, then you must repeat both of the vertices on that edge. Okay, so a path has no repeated vertices and no repeated edges as well. A closed walk is a walk that starts and ends at the same vertex. A circuit is a closed walk that contains at least one edge and does not contain a repeated edge. It can repeat vertices, but not edges. And then a simple circuit is a circuit that does not have any other repeated vertex except for the first and the last. Okay, so a simple circuit is like a closed path, basically. I'm actually kind of disagreeing with the wording that the author chose to use for simple circuit. This is something that is usually called a cycle. That's the more common terminology. In fact, I've only ever heard it called a cycle. But anyway, we'll go with this terminology in the textbook, simple circuit. Okay, so here is a little table here that organizes what all of these different things are. So you see with a walk, you're allowed to do anything you want. You can repeat an edge, you can repeat a vertex, you can start and end at the same point if you want, and you don't even have to include one edge. You can just stand still and still be a walk. A trail is no repeated edges, but you can do anything else. A path is no repeated anything, and it does not start and end at the same point. And it does not have to include at least one edge. Closed walk is you can repeat anything you want. You must start and end at the same point. That's what makes it closed. And it does not have to contain at least one edge. So it can be a trivial walk. A circuit No repeated edges, but you can repeat vertices. You must start and end at the same point. That's the idea of a circuit, is that it's closed. And then it has to include at least one edge. And then simple circuit is no repeating. You can only repeat the first and last vertex by closing the loop. And then it is a closed path, closed circuit, so it does start and end at the same point, and it must contain at least one edge. Okay, so these are a little bit troublesome, all these definitions, but let's go ahead and try to apply them to some problems. Okay, so let's try this here as an example, number 2. So in the graph below, determine whether the following walks are trails, paths, closed walks, circuits, simple circuits, or just walks. Okay, so let's look at part A here. So I'm starting at V1, and then I'm going along E2 to V2, and then I'm going along E3 to V3, and then along E4 to V4, and then along E5. Okay, so I've repeated a vertex here to V2, and then I'm going along E2 again up here to V1. So I'm back here, and then I'm going along E1 to V0. Okay, so you see that I did repeat an edge, and I repeated some vertices, and it also did not begin and end at the same point. So I believe that is just a walk. Okay, so that was part A. Let's do part B. So part B, I start at, so actually they've only given me the vertices in this one. So let's see if we can figure out what the edges were without looking at what they actually were until we see them on the graph. Okay, so we start at V2, and then we're going to go to V3. So I'm going up here. I must have gone along E3. And then I'm going to V4, so I must have gone along E4 there. And then I'm going to V5, so I'm going over here. And then I am going back to V2. Okay, so this is closed, and I did not repeat any edges, and I only repeated the first and last vertex. So that is actually a simple circuit. I'll just abbreviate it there. Okay, let's look at part C. Okay, so part C, I start at V4, and then I go to V2, so I must have gone up there, and then I'm going to go to V3, so up there, and then I'm going to V4 again. Okay, so I've repeated a vertex, and then I'm going to V5, okay, and then I'm going to V2, all right, I'm repeating that vertex again, and now I'm going to V4. Okay, so I did repeat an edge, and I repeated several vertices. But notice that I did begin and I ended at the same spot. So that is actually going to be a closed walk. I'll just abbreviate it. Oh, that's not a very good abbreviation. Okay, let's try it like this. CW, closed walk. Okay. All right, let's look at part D. So starting at V2, and then I'm going to go to V1. Okay, and then I'm going to V5, and then I'm going to V2. Okay, so I've repeated a vertex. And then I'm going to V3, and then to V4, and then back to V2. Okay, so notice again here, I did begin and end at the same one, so that is closed. So it's either a closed walk, a circuit, or a simple circuit. It definitely can't be a simple circuit because I repeated a vertex in the middle there, V2, not just at the beginning and the end. But I didn't repeat any edges, so I think this is going to be a circuit. So this is a circuit. Okay, and let's look at part E. So I start at V0, and then I go to V5, and then I go to V2, and then I go to V3, and then to V4, and then to V2. Okay, so I've repeated a vertex, and then to V1. Okay, so I repeated a vertex, but I did not repeat any edges, and it was not closed, so that is going to be a trail. All right, and let's do the last one. So I start at V5, and then I go to V4, and then I go to V2, and then I go to V1. Okay, so I didn't repeat anything here, but it's not closed, so that is going to be a path. Okay. All right, so here's one for you to try. Go ahead and pause the video and try this one, and check your answer in the back of the book. Okay, so now let's look at another definition related to graphs. Let G be a graph two vertices v and w of G are connected if and only if there is a walk from v to w. The graph G is connected if and only if, given any two vertices v and w in G, there is a walk from v to w. So symbolically, we say that G is connected if and only if, for all vertices v, w in the vertex set of G, there exists a walk from v to w. So just let me draw you like a little small example here. So a connected graph would be something like where all my vertices I can get from any of them to any other one. So for example, like this, I can go from any vertex to any other vertex. And then one that would not be connected, for example, would be something like this. So I can get between these two, but I can't get to these ones over there because I have not connected those two parts of the graph. Okay, so let's look at an example in a homework problem. So I'm going to do part B here. An edge whose removal disconnects the graph of which it is a part is called a bridge. Find all bridges for each of the following graphs. Okay, so let's look at B here. So which of these edges would disconnect the graph? So if I look at this edge right here, for example, even if I take this edge out, I can still make it from V7 to any of the other vertices, and I can make it from V0 to any of the other vertices. So that would not be a bridge. But for example, right here, if I take out this edge, then I would disconnect V8 from the rest of the graph. Similarly, if I take out this edge, I would disconnect V2 from the rest of the graph. And if I take out this edge right here, I would disconnect that little triangle over there would be disconnected from the rest of the graph. So I believe those are the only three bridges. So go ahead and pause the video and try doing part A, and then check your answer in the back of the book. Okay, so now let's talk about a special type of circuit, and this is actually going to relate us back to the 7 bridges of Königsberg problem. So let G be a graph. An Euler circuit for G is a circuit that contains every vertex and every edge of G. That is, an Euler circuit for G is a sequence of adjacent vertices and edges in G that has at least one edge, starts and ends at the same vertex, uses every vertex of G at least once, and uses every edge of G exactly once. So exactly once here means you cannot repeat them. So it is going to be a circuit, and then it is in particular the type of circuit that goes through every edge in the graph. And if you've gone through every edge of the graph, then you need to also go through all of the vertices in the graph as well. Okay, so let's try doing some problems related to this. All right, so let's look at this example here. So we have to determine whether or not this has an Euler circuit, and then if it doesn't have one, we have to explain why. And if it does have one, then we have to describe it. So let me try drawing an Euler circuit here, and I'll show you what can go wrong. So let's say I start at X over here, and I just start going up. Oops, my pen is messing up. Oh no. Okay, there we go. So if I start going up from X to W, and then I go to U, or sorry, that's a V, and then to U, and T, and S, and R, and Z, and Y. Now if I come back to X, then I'm not going to be able to get to the rest of the graph. So I don't want to go straight back to X. Maybe I need to like detour a little bit. So I could go maybe like this. Boop, boop, ba-doop, ba-doop, ba-doop. Okay, so that would have been an Euler circuit. I think I see like a little more efficient way of doing one. So if I start at U and I just go around the graph like that on the outside, and then I go around this triangle, and then I go around this triangle, I think that's another way of doing it. There's probably a lot of ways of doing it. So let me try right down that path. So starting at U, and then T, S, R, Z, Y, X, W, V, and then back to U. So that's around the outside. And then around one of the left triangle, then I would go to S, Z, and then back to U. And then around the right triangle, I'll go from to Y and W, and then back to U. Okay. So let's talk about when Euler circuits exist and when they don't. So here's a theorem for us, and I'm not going to prove this theorem, but I'll talk a little bit about why it is true. A graph G has an Euler circuit if and only if G is connected and every vertex of G has positive even degree. So the part about it being connected should make sense because you're not going to be able to go around to every vertex in a circuit unless the graph is connected. If some of them are off, in the distance that you can't reach, then obviously your circuit's not going to be able to make it there. And then the part about all the degrees being positive and even. So firstly, the word positive there is just trying to eliminate the possibility that any of them have 0 degree. That's kind of covered by being connected, though, I think, so that wasn't really necessary. But the even part here is important. So what happens in a graph with even degree is that, for example, if the vertex has degree 2, like this one that I've just drawn, then you can enter the vertex and you can exit the vertex, and that's going to cover both of those edges. And then if it has degree 4, for example, then you can enter along one and then exit along another one, and then you can come back later and enter along one and then exit along another one. But what happens, for example, if you have degree 3? So you can enter and you can exit along 2 of them, but then if you come back because you have to get that last edge at some point, then you're going to come back and you're going to be stuck there because you won't be able to do any of the edges more than once. So you would have to stop, right? Does that make sense? And likewise, if you have just one edge, then you can go there, but you can never leave because you can't traverse that edge again. So that's the meaning behind this theorem. And like I said, I'm not going to do a big formal proof of it, but that's why it makes sense. So let's do some problems where we use this. Okay, so let's look at this graph right here and think about whether it has an Euler circuit. So you could just start trying to draw an Euler circuit. So for example, I could try to draw one starting around here. So that covers that part. And then maybe I could go around here, and then down here, over here, over here. So at some point I'm going to get stuck though, because like for example, here, now where do I go? I can't exit V7 to get back up to that other edge that I missed because there's no other edge out of V7 that I can exit it by. So you see the problem that happens in this graph right here actually has to do with this vertex right here and this vertex right here and also this one here, and actually there's a whole bunch of them, right, that have odd degree. So those 4 vertices right there are making it actually impossible for this to have an Euler circuit because they have odd degree. So these vertices have odd degrees, so there is no Euler circuit. Okay. So here are a couple of homework problems for you. So look at these, see if all the vertices have an odd degree, if any of them have an odd degree, or if they all have an even degree. And if they all have an even degree, then you can try to find an Euler circuit. So go ahead and give this a try, and then check your answers in the back of the book. Okay, so now let's talk about Euler trails. So Euler trails are very similar to Euler circuits, except they're trails. So let G be a graph, and let V and W be 2 distinct vertices of G. An Euler trail from V to W is a sequence of adjacent edges and vertices that starts at V, ends at W, passes through every vertex of G at least once, and traverses every edge of G exactly once. So basically they have the same properties as an Euler circuit. They visit all of the things in the graph, they visit all the edges once, and then all the vertices at least once, but it's a trail rather than a circuit. So we have a corollary here that tells us when these two things, when this thing exists, and this is a corollary to a proof that I'm not going to show you, but we can just use this information. So let G be a graph, and let V and W be 2 distinct vertices of G. There is an Euler trail from V to W if and only if G is connected, V and W have odd degree, and all of the vertices of G have positive even degree. So if you have just 2 vertices that have odd degree, then you can do an Euler trail between them, as long as all of the other vertices have even degree. And that kind of makes sense because when you're thinking about the idea of like stopping and starting, you can, for example, you can just leave V once and then just enter W once. Then if V has like more edges coming out of it, like say they both have 3, then I can leave V once and then come back once and then leave again once. And then for W, I could like come to W once and then leave again and then come back once and stop. So hopefully that makes sense to you. Also, there was a typo in the book where the author called it an Euler path on this corollary. that is a word that exists. Some people do call them Euler paths, but I think that is actually not what she meant to say. I think she meant to say trail, since she never defined an Euler path. Okay, let's look at some problems. Okay, so for each of these, let's try to determine whether there is an Euler path from U to W, and if there is one, then let's find it. Okay, so where are U and W? So here's U, so here's where we're going to start, and then W is here where we're going to stop, and then those both have odd degrees, so that works, but I see another couple of vertices that also have odd degree, so that is not going to work. So H and E have odd degree, so this is not going to work. Oops. So there's no Euler path here. Okay, let's look at the other one. So U has an odd degree, so that works, and then W has an odd degree, so okay. And then the rest of them, let's see, they look like they all have even degree to me, the rest of them, so let's try finding an Euler path from U to W. Okay, so let me see what I'll do here. So I guess I'll just go up to V0, and then I'll go over here to V7, and then I'll go to V6, and then maybe I'll go back down to W, and then over to V5 and V4, and then let me try taking this little zigzag path. Oh, no, that's not going to work, is it? Okay, let me try going up here, and then over there, and there, and there, and then down here. Okay, and now I can zigzag back to W. Okay, so let me try writing down that path. So that's U, and then V0, V7, V6, W, V5, and then V4, V3, V2, V1, and then I went back to U, and then I went to V3 again, and then V6, and V4, and then W. Okay, I think that's what I did. You guys can check me. Okay, so here's a homework problem for you. So figure out if this has an Euler path from U to W, and if it does, then write one down. This should be trail. Sorry, I just made the same mistake as the author. Trail. Okay, so last concept for today is Hamiltonian circuits. So given a graph G, a Hamiltonian circuit for G is a simple circuit that includes every vertex of G. That is, a Hamiltonian circuit for G is a sequence of adjacent vertices and distinct edges in which every vertex of G appears exactly once, except for the first and last, which are the same. Okay, so we're not allowed to repeat vertices. We were allowed to do that in Euler circuits, but not in Hamiltonian circuits. So we have to visit every vertex exactly once. And then, of course, that means that we also can't repeat edges, since if you repeat an edge, you would have repeated the vertices of the edge as well. So let's give this a try. Okay, so let's try finding a Hamiltonian circuit here. I'm going to do 24, and then 23 is your homework problem. Okay, so I think I'll just try to go around the outside, maybe from B to A, L, K, J, E, D, C, and then let's see. Okay, I see how I can do this. So I'll go to F, and then I, H, G, and back to B. Okay, so that takes me through all of the vertices once, and I don't have to do all of the edges, I just have to do all the vertices. So let me try writing this down. B, A, L, K, J, E, D, C, F, I, H, G, and back to B. Okay, so you try doing it with yours, see if it works or not, and if it does, then write down the circuit. Okay, let's try a couple more. So I'm going to do both of these as examples here. I believe these are ones where I can't remember if they exist or not. Let's find out. Okay, so let me try doing the one on the left first. So I'm going to start at V6, then V2, V1, V0, V3, and then let's see, V7, V4, V5, V6. Yeah, so that works. Okay, so let me write that down. Okay, now let's look at the one on the right. I believe this is the one where it does not work. Okay, so let me try to explain why this isn't going to work. So we have to visit D at some point, right? And there's only one way to get in and out of D, So in order to include D, I have to include these two edges right here. And then we also have to visit B at some point, right? And there's only one way to get in and out of B. So in order to get in and out of B, we have to visit these two edges right here. Okay, but now what you see is we've already made a simple circuit. That, just those four edges right there, that is a simple circuit, and we cannot add anything to that. Because if we added anything to that, we wouldn't have a simple circuit anymore. We would have a circuit that repeated vertices or edges. So there is no way to get to E, F, H, and G without repeating some vertices or some edges. So let me just write that down briefly. Okay, so here's one last homework problem for you. So try to find a Hamiltonian circuit here, and then if you cannot do it, then explain why you can't. Okay, that's it for today, everybody. So I'll see you guys next time.